This is going to be my introductory lecture to the pH laboratory. Now, all of you have been through the instruction in Module 2, Topic 4 on pH, so you've seen this diagram already. It's a very important one. It shows the ionization of water, which basically means that we're going to be taking water molecules which are uncharged, not ions, and we're going to be seeing how they form ions, a hydronium ion and a hydroxide ion. And the basic idea here is that this hydrogen nucleus right here is going to jump ship. It's going to leave the right-hand water molecule and it's going to jump over to the left-hand water molecule, and it's going to become H3O. And because the hydrogen nucleus, which is a proton, is going over to the left-hand molecule without carrying its electron, there's going to be a net positive charge on the hydronium ion, and the structure on the right, the hydroxide ion, will have a negative charge because it will be keeping the electron that this proton left behind. Okay, and this is the we refer to this as a dissociation of water because sometimes we think of it as a water molecule that is simply having the hydronucleus break off, and what's left behind is an OH molecule. I typically depict this in a chemical formula. It's very well known. H2O, water molecule, is dissociating into two structures. The typical picture is for us to talk about OH. It's a hydroxide ion, which is going to carry a negative charge. And instead of talking about hydronium ions, we generally talk about hydrogen ions, which are just H+. And it's not entirely accurate, but it's close enough. It gives us a pretty good picture of what's going on. Okay, so this is the dissociation or ionization of water. And while this is happening, the hydroxide ions and hydrogen ions that are there in water are also reassociating. We have the reverse reaction taking place in which some of these are disappearing. They're not really disappearing. They're basically forming back their water molecule structure. Okay, and there's also going to be the steady state of concentrations because the forward reaction, the reaction going from left to right, is occurring at exactly the same pace as the reaction going from right to left. We're left with a constant concentration of both hydrogen ions and hydroxide ions in the solution. And so here's where we come to the concept of pH. Not directly, it's kind of convoluted how we get there, but we say that when we think about pure water, okay, it's never really pure water, it's never really pure H2O because there's going to be some concentration of OH minus and H plus there as well because of this property of ionization of water. However, in pure water, we know that when the steady state is reached, there's going to be a concentration of 10 raised to the minus 7th moles of H plus or OH minus per liter of solution, per liter of pure water. Okay. And you might want to remember that a mole is actually 6.01 times 10 raised to the 23rd. That's a chemical number. It's Avogadro's number. And so in actual fact, the total number of hydrogen ions that are there in 1 liter of water is roughly 6 times 10 raised to the that would be raised to the 17th power, or 16th power, sorry, which is actually a huge number. It's basically 6 followed by 16 zeros. That's the number of hydrogen ions there are per liter of water. And they're also 6 times 10 raised to the 16th power, 6 followed by 16 zeros. Concentration. The concentration is the same of hydroxide ions. So we've got that many of these guys per liter, that's many of OH minus per liter. And these two things are in balance, and there's no net excess of either hydroxide ions or hydrogen ions in the solution. Okay. Now that might seem like a lot, but basically what we're saying here is that this concentration, this number of moles per liter of hydrogen ion, is going to differ according to the pH of the solution. Okay, if we have a more acidic solution, more acidic solution, the concentration is going to be greater than 10 raised to the minus 7th moles per liter, right? More basic, the concentration of hydrogen ions is going to be less than 10 raised to the minus 7th moles per liter. And what the pH scale does is basically, it basically keeps track of this number right here, the negative exponent in the concentration in moles of hydrogen ion there is in solution. So what we're saying here is that if we have a pH of 7, pH 7, which is the pH of pure water, we're saying that at steady state, the concentration of hydrogen ion is going to be 10 raised to the minus 7th moles per liter. Okay. Now, if we were to have a concentration of hydrogen ion that's 10 times greater than that, and here's where people sometimes get confused, because 10 raised to the minus 7th is equal to 0.0000001. Okay, that's the number. If we want to make 10 times greater than that, so 10x, 10 times 10 raised to the minus 7th, that's going to be moving the decimal place over by 1, and so this is going to be 0.0000001. Okay, and so this is also going to be 10 raised to the minus 6th. So basically what we're saying here is that if the concentration of hydrogen ion is 10 times greater than a pH 7, then the concentration is going to be 10 raised to the minus 6th moles per liter of hydrogen ion, and this is going to correspond to pH 6. Okay? And by that virtue, pH 5 is going to be 100 times. It's going to be 100 times greater in terms of its hydrogen ion concentration than pH 7. Okay, so what's kind of crazy here is that as the acidity of a solution increases, pH is actually decreasing. So pH 5 is more acidic than pH 6, pH 6 is more acidic than pH 7, and so forth. Okay, a really strong base would be something like pH 2, hydrochloric acid. The hydrochloric acid that we'll be using in the laboratory will have pH 2, and it's going to be a very, very low pH. Your stomach acid is roughly at pH 2 because of the high concentration of hydrochloric acid there. Okay, so this would be a very acidic. Okay, now that is basically covering part of the story, and I hate to bring up English grammar here, but we've got two different very similar words. One is the concept of acid, which is basically a substance that makes things more acidic, and the other one is the adjective acidic. And what we've done so far is we've described what it means to be acidic, which basically means to have a high concentration of hydrogen ion. But we really haven't talked about acids, and it's really kind of a basic thing. Acids are substances that make things more acidic. In other words, they create a situation with higher concentrations of hydrogen ion, and therefore we say that these guys are hydrogen ion donors. Sometimes they call them as proton donors. And so this is part of the story. You could say, well, how do we make a pH 5 solution starting with pure water? Well, you could take pure water and add an acid to it. The acid will release hydrogen ion, and then you would end up with a much higher concentration of hydrogen ion and a much lower pH. A good example of an acid would be HCl, hydrochloric acid. And what happens is that this substance, this acid, is going to be dissolved in water. And when we dissolve it in water, the hydrogen ion dissociates from an otherwise stable chloride ion. Chloride ion is released, simply floats around in the water, and the hydrogen ion is simply there and has the effect of increasing the overall concentration of hydrogen ion. Okay? So I got that. There are two different concepts here. One, the first concept we discussed was the idea of what it means to be acidic. The second concept was basically what is an acid substance. Okay? Slightly different, but there's a real important distinction that you have to understand there. Okay. Now the opposite side of the pH scale, it will be one in which we can talk about basicity or alkalinity. You can have basic solutions or alkaline. Okay, would be these are adjectives that describe pHs that are greater than pH 7. The pH number is greater than pH 7, and if this happens, we're going to have a concentration of hydrogen ion that's actually far lower compared to what we have in the case of water. Okay, so the general idea here is that as the hydrogen ion concentration changes, for example, if we were to make the hydrogen ion concentration 100 times higher, therefore making our solution a pH 5 relative to pH 7, then the hydroxide ion, OH minus, is going to be lower in concentration, and its factor of difference, the relative concentration compared to the pH 7 is going to be by the same factor. So OH is going to be lower by 100 times as well. Okay, the opposite is true. So if we were to increase the concentration of hydroxide ion, the outcome would be automatically a decrease in the hydrogen ion concentration. So for example, in the same way that if we were to add hydrogen ion with HCl, the pH would be decreasing because the hydrogen ion concentration would be increasing. If we were to take a substance like sodium hydroxide, NaOH, and add it to the solution, what's going to happen is that it's going to dissociate lots of OH minus into the solution, and it's going to also have the Na plus. Na plus will be the sodium ion that freely floats around. This is going to have the effect of decreasing H plus, and it does so in this almost perfectly symmetrical way. If you were to add equal concentrations of NaOH and HCl to pure water, what would happen? Well, I think it would make perfect sense. You would have Na plus, that's the sodium ion coming away from sodium hydroxide, the OH minus coming away from sodium hydroxide. You would have the chloride ion coming from the hydrochloric acid, and the H plus coming from the hydrochloric acid. And these two parts over here would combine to form pure water. These two out here would basically be regular old table salt. And we would restore the overall concentration of hydrogen ion back to its steady state that we find in pure water. And we could get to a pH of 7 with NaOH added and HCl. NaOH added together with HCl. Okay. And therein lies the core idea behind the concept of titration. Okay. If you have a substance that is that starts off as acidic, you could neutralize that entirely by adding a very specific quantity of base. So if we start off with an acidic solution, maybe because we have added HCl to a solution, we could turn that acidic solution into a perfectly neutral solution by adding just the right amount of sodium hydroxide. Okay, so basically, the world of titration is kind of similar to an old Tootsie Pop commercial where you have to measure the number of licks it takes to get to the chocolatey core of a Tootsie Pop. Here we're basically having to measure the number of drops it takes to cause our originally acidic solution to reach perfect neutrality. All right. So start off with the known volume of your acidic solution, count the number of drops of NaOH that it takes in order to reach neutrality, and when it turns from acidic into neutral, then you know you've hit the right number. Okay, similarly, if you start off with a basic solution, you could be adding HCl to reach neutrality. And so, but let's talk about this. I guess the big question here is, how do you know when your solution is no longer acidic? And here's where it comes, here's where we pull up the mean scientific tricks. And the first trick is to add a substance called phenol red. We really should call it phenol yellow initially because it starts off as a yellow color. The reason for this is phenol red is an indicator that changes color. As it's acidic, when it's acidic, it's in the yellow state. But once the pH goes above a certain point, once it goes above approximately neutral, the color turns to a red color. So you might notice that our HCl solutions that you're going to be practicing your titration with are starting off in a yellow color. And so what you'll do is you'll add 2 ml or 4 ml of this originally acidic solution, and you're going to be adding NaOH to it, drop by drop, drop by drop, drop by drop. You have to stir after a while, and basically have to add a drop, stir, add a drop, stir. But when you reach the point where it permanently turns into a pinkish color, or better yet, kind of an orangish color, just right where if you add one more drop, it's going to turn pink. That would be the turning point. That would be the point at which you would have a neutral pH. If it actually goes all the way pink, then you're dealing with a basic solution, and you've kind of overshot the titration. Okay, and so yeah, you add if you start off acidic, you add the base until you reach that turning point and count the number of drops. That's going to be your measure of acidity of the original solution. If we start off with an originally basic solution, then instead of adding NaOH, you'd be adding HCl of known concentration. You count the number of drops and add them drop by drop. And when you reach the turning point, the solution turns permanently to yellow, or better yet, to that same orange color, which kind of represents the halfway mark, the in-between state between acidity and basicness. That would be the point of neutrality. That would be the number of drops you would record to determine the amount, the relative alkalinity of the solution. All right, so that should be enough to get you started. I know I've skipped over some things. There are probably going to be some other things I need to add as we work through our laboratory. But you will be able to, we'll cross those bridges when we come to them.